Hello students, welcome to 18th video lecture of electrostats. This video lecture I have created especially for electric field intensity due to a uniformed charge thin spherical shell, right? Officially this topic, I told you in the last video lecture that this topic is not there in the syllabus. Now it has been excluded, but we have to study because applications are there. So let's start. Now if we consider a point P outside the shell, then what should be the electric field intensity? Let us understand. Let us have a positively charged spherical shell, its center O and its radius R. It's hollow because the spherical shell is hollow inside. Now the total charge, amount of charge on the spherical shell is Q. Let us consider a point P outside the shell, and let us assume a Gaussian surface, which is a sphere over here, okay, which is passing through the point of consideration where we have to calculate the electric field intensity, right? Now Gaussian surface radius R we have assumed. This is small r. Capital R is the radius of the spherical shell. Now let us choose a small area over here so that we can integrate and calculate the net electric field intensity, right? Now this is the area vector of this small surface area, vector ds, and electric field intensity normally outward because of these positive charges. Both are in the same direction and acting at 0° angle. So from Gauss law, phi integration over whole surface, vector E dot ds is equal to q upon epsilon naught. Let us apply this. Since E and ds are in the same direction as we have discussed just now, the phi is equal to E ds because cos 0 will act over here, cos 0 1. So therefore integration E ds is equal to q upon epsilon naught, right? Or E outside, integration of ds is equal to q upon epsilon naught, right? And now this ds, when we'll integrate, then we'll obtain the total surface area of this Gaussian sphere, right? So E into 4 pi r square, remember here is small r because we have integrated the area of this Gaussian sphere, right? 4 pi r square is equal to q upon epsilon naught, or E is equal to q upon 4 pi epsilon naught r square. And if you remember, this is the electric field intensity due to a point charge formula. So therefore we can further write q is equal to sigma into 4 pi r square. Sigma is the surface charge density, so q is equal to sigma a. So therefore we can write sigma r, capital R square upon epsilon naught r square after putting the value of q from this expression, okay? So electric field due to a uniformly charged thin spherical shell at a point outside the shell is such as if the whole charge were concentrated at the center of the shell. Just now I told that this formula is for electric field intensity due to a point charge, and we are getting again the same formula for this spherical shell. So therefore we can give this a statement that electric field due to a uniformly charged thin spherical shell at a point outside the shell is such as if the whole charge were concentrated at the center of the shell, okay? So the center we can assume as if the whole charge is concentrated, the total charge q is concentrated at this particular point, then only we are getting this kind of formula, okay? Next, at a point A on the surface of the shell, that point P we considered outside the shell. Now we are going to consider on the surface of the shell. Let's assume same sphere. Now this point A we have assumed on the surface of the spherical shell. Now this time the Gaussian surface will be the spherical shell itself, because this point is lying on the surface of the spherical shell, right? Let us assume a small area over here again, vector ds normally outward, and again electric field intensity in the same direction. Okay, so from Gauss law we can write this expression as we have written in the last slide. And again we have got that situation that E and ds both are acting in the same direction, so 0 degree angle. So we can write integration E ds is equal to q upon epsilon naught, or E integration over whole surface ds equal to q upon epsilon naught. This time ds will be integrated for this spherical shell, so this radius we will use. So now E into 4 pi capital R square is equal to q upon epsilon naught, or we can write E is equal to q upon 4 pi epsilon naught capital R square. Okay, again we can use q is equal to sigma A, and A is equal to 4 pi R square total surface area. So therefore we can write E is equal to sigma upon epsilon naught after putting this value of q over here. Okay, so therefore electric field due to a uniformly charged thin spherical shell at a point on the surface of the shell is maximum. It is independent of R, so that's why it is maximum, right? Next, now at a point P inside the shell, now we are going to consider a point which is inside the shell. Let us assume the spherical shell once again and assume a point B which is inside the shell. Now this time we have to assume a Gaussian surface, okay, which is which passes through this point B and lying inside the spherical shell, right? Now this radius of this Gaussian sphere is what? Small r. Now small area, vector ds acting in this direction, and electric field intensity again in this direction, because in that formula we obtained the situation that in the first particular derivation, or we can say in the first case where the point was considered outside the shell, we obtained the formula similar to the formula of electric field intensity due to a point charge. Okay, so therefore the electric field intensity is acting in which direction? Normally outward direction through the center. Okay, so from Gauss law again we can write the same expression, and E ds both are in the same direction. So again we can write the same condition or same formula as we have proceeded in the last two slides. Now we can write E integration of ds is equal to q upon epsilon naught. Again this time we have considered this is actually r dash, not r, so r dash square, surface area of this small sphere which is a Gaussian sphere, or we can write E is equal to 4 pi epsilon naught r dash square, E is equal to 0 upon 4 pi epsilon naught r dash square. Now you can see 0 is written here. If you go to the definition of Gauss law, this q is the net charge enclosed inside the Gaussian surface, but here you can see in this Gaussian surface no net charge is physically enclosed. Okay, this sphere encloses no charge. Charge is situated outside the Gaussian sphere, so therefore q net inside this particular Gaussian surface is 0, so that's why we can write like this. So same thing is written over here, since q is equal to 0 inside the Gaussian surface, therefore we can write E is equal to 0. So electric field intensity inside the spherical shell is equal to what? 0. So we can say this particular region inside the spherical shell is protected from electric field. There is no electric field inside the spherical shell, right? So these were the situations which we discussed for spherical shell, 3 situations. And finally this property is equal to 0 inside a cavity is used for electrostatic shielding, as I told just now that inner part of a spherical shell is protected from electric field. So due to that protection, this phenomena is called as electrostatic shielding. Okay, because this cavity has no electric field, so this cavity is shielded from electric field, that's why it is called as electrostatic shielding, right? Now we are going to plot a graph between E and R for a spherical shell. E is electric field intensity and R is the distance. Okay, now we can assume this particular origin as O. Let us see the graph. This is a rectangular hyperbola, but it is not starting from this particular point. Why? Because it is not electric field is not found inside the spherical shell. So therefore in this particular region shows inner region of spherical shell. So therefore the electric field starts from here, and since it is inversely proportional to R, so therefore it is decreasing, and this particular distance is what? R. Capital R, you can see capital R is the radius of the spherical shell. So within the radius there is no electric field, so therefore there is no graph variation is there in this particular region. So electric field inside the spherical shell is 0. That this particular statement is shown through this particular region of the graph, and from surface to outside any point this region is there, right? Okay, and maximum electric field intensity at the surface. So this particular point of the graph shows the electric field intensity on the surface of a spherical shell that we have shown in the last slide, right? So this is the end of this discussion, that electric field intensity due to the uniformly charged spherical shell, and we can say a major part of electrostats has also come to an end. Now from next video lecture we will proceed to the another part of electrostats. This is the first half, and that will from that next video lecture we will start from the second half part of the electrostats. So till that time, keep on studying, keep on revising. Thank you so much for paying attention.